Okay. Hello, welcome everyone for our second part of forensic analysis. So this is our fifth session, and in this session we'll be recapping some of the more advanced types of forensic analysis that we can do with Velociraptor. In the last session we just had the basic ones, which are most commonly used: the searching for files, the NTFS type artifacts, and then today the artifacts are much more specific, but also very useful. And perhaps they're also very useful. So let's just dive straight in. Okay, so today we're going to look at some of those advanced capabilities, and a really good framework to understand that is the MITRE ATT&CK framework. And so there's a link here, and you probably have heard of that. And essentially, it's just a way of of organizing different kinds of attacks and different kinds of techniques. So we will use it today and tomorrow to kind of guide us a little bit. The first thing that I wanted to talk about is specifically the evidence of execution. And this kind of investigation is very common if you want to know whether a program executed or ran on an endpoint. So there's a number of reasons for a program to run. For instance, a lateral movement, an attacker has laterally moved across the network and then caused particular programs to run, for example, PSExec or Command Shell or PowerShell or other things like that, like the sysinternal tools or things like that. And on the other hand, you could have something like drive-by downloads that caused some kind of malware to be dropped on the machine, and you want to know whether that executed. So there's a whole bunch of kind of related artifacts to do with execution. Now, if you have a look at the SANS poster, so SANS do a whole bunch of courses that cover the basic forensic artifacts that are left behind. And they have a very nice poster, and it's actually linked off this slide. You can download it. But it actually covers, it kind of tries to organize all the different artifacts in a topic, so topical sort of way. So for example, like all the ones that are useful to determine whether a file was downloaded here, all the ones that are useful for determining whether a program executed are here. So these are all very details, and I mean, the SANS courses go into a lot of detail about all the different artifacts. But the whole point of Velociraptor is that we don't really need to worry about it too much. So all of these things, or a lot of these things, become artifacts that we can just select and collect from the endpoints. And so that allows us to kind of build on that knowledge and then just kind of get the results that we wanted to. So in here, in this slide deck, I've got a whole bunch of ones that are circled, but there are other ones, and there are artifacts to cover other ones. And if one of them are missing, then we can always write artifacts for it. So let's look at a particular example of this. How do we determine if a binary was run? Okay, so the first kind of artifact that I wanted to talk about is the prefetch files. And prefetch files are actually kind of an optimization for performance. So there is actually a prefetch folder. It was introduced, in Windows 7. There's a prefetch folder in Windows, and it just has a bunch of these PF files. So let's bring up a command prompt, and we can have a look at it. So basically, you can actually just see them, prefetch, right? So Windows prefetch, and then there's all these .pf files in there, and you can see that the name of the file it looks like an executable, and then it looks like this is a hash, sort of like a 4-byte hash, and then it just has a .pf file. Well, it turns out that those PF files they keep records information about. It's like a little database. It just keeps information about when the program ran last. So first off, every time the program is executed and a binary is executed, the prefetch record is updated in the prefetch file. So the first thing you notice is that there is actually a timestamp on just the file, right? Because the file itself has been modified. So that's the first. I mean, even without having a look at the internal structure of the file, we can immediately see that there's a timestamp here because obviously the file's changed. So let me just show you real quick how you would collect prefetch files and analyze them. So let's start up our Velociraptor instance as we normally do, and we're just going to use the same way that we've done before. Just run our Windows GUI, right? Velociraptor for Windows GUI, and that will just bring up the normal UI as we've done before. But this time, what we're going to do is we're going to find our machine, our client. And again, when you run the GUI command, it just creates a local client so that we could talk with it. And we could click our collector tab, and now we can just select prefetch. So we're going to add a new collection, prefetch. There's actually a couple of different types of prefetch, a couple of different artifacts. Let me just show you this artifact first, forensic flow prefetch. So this one, you can see that there's a bit of explanation here. And then we have some parameters here. So where we're going to collect the prefetch files, and over here there's the VQL, but we won't really worry about that too much for now. Let's configure the parameters. So we can actually limit the dates and times here and the binaries if we wanted to. But for this exercise, let's just collect the defaults. So it's just going to parse all the prefetch files, and we'll just see what kind of results we're getting. Okay, so if we just collect that from the endpoints, it should take a couple of seconds maybe. And there we go. We got some results now. Okay, so we can have a look at. Let's just remove some of these because, oh, well, yeah, I mean, we can scroll, I guess. So we can see, so question, does Velociraptor collect raw prefetch files and parse them on the server, or does it parse them all on the client and sends the data to the server? That's an excellent question. So Velociraptor actually parses the prefetch files on the endpoint. But as you can see, if we just copy this collection, there is, sorry, it is already actually, we can upload them. We can grab the actual files if we needed to, but it parses it on the endpoint. If we wanted to actually grab the files, there's a bunch of, the cape artifact allows us to just grab the prefetch files themselves. But generally, we just parse them on the endpoint and we return, just parse and return the result set. So in this particular one doesn't upload, this artifact doesn't really upload it. So you can see that the times are coming back parsed, right? So we parse them on the endpoint and send back the results. Now inside of each file, you can see that we have here, we have the last run times. So in each prefetch file, it stores up to 8 timestamps of when it was run last, this executable. Now, the thing to note is that once you go over 8, then it kind of wraps around, right? So it only stores the last 8. So then you have the run count, which is the total number of times this executable was run, And so it can go more than 8, right? So if it's a frequently run executable, like this one's 23, but we only have, 8 stored, right? So because it's Chrome, so every time Chrome runs, then it has, increases that, but it only stores the last 8. The other thing that's interesting is that we only have the name of the executable, so we don't have the path, the full path here. And here we know the path of the prefetch file. And then you can see that some of them have a duplicate, not all of them, but some of them have a different hash. So that hash is, see if we can see a few that are, yeah, I mean, this one is the first Chrome setup one. This is chrome.exe. Yeah, and so you see this is the hash of 052. Yeah, I think this one repeats the timestamps. So you can also collect the second one, and you can see that this is difficult to parse because it has like an array of times here, and the other prefetch, it's basically builds a timeline. So what that means is that each of those times is repeated to create multiple rows, and that makes it a little bit easier to delimit the times that you're interested in. So I'll just collect that one and show you the difference between the two. So this one is basically just parses the prefetch file, the whole file, right? One per row. And so it ends up with these are kind of like an array. But this one just splits, repeats that line so that you end up with a single time for each row. That makes it a lot easier to filter because, because you can basically, limit the times here, right? Because it creates sort of like a timeline, right? With the event time, and then you can sort and order by the event time and so on. So the timeline one is more suitable for figuring out the different times. So that's the prefetch one. So there is a prefetch parser, built in, obviously. So it parses it on the endpoint. So you don't really need to collect those files. And so it means that, if you have an incident and you know exactly the timestamps, the time range that you're interested in, you can just straight away, delimit it and filter it. So, like in this case, we could say, it's got to be date after, we'll use like a couple of weeks ago. And then when we launch it, then it will only return those times that are relevant, like 2 days old or whatever. So all the executions from, so there's a lot less. And this is more suitable for doing a hunt. So when you have a big network, and then you just want to bring back all the executions that happened in a time range rather than all of them. And so it reduces the total number of rows that you need to look at. So this is why it's much. So again, it doesn't do that on the server. It does it on the endpoint itself and return the results. So that's prefetch. Again, there is there is not a lot we can say. It actually also stores in the prefetch binary parser. It also stores the file names. You can actually tell the path, the full path of the file. But you have to modify the artifact a little bit. So maybe we can leave that as an exercise, actually. So I think that was that's in I think it's been recently fixed to allow for these additional information. Or it will be fixed. But you can actually get, so in the prefetch file, it also stores DLLs and executables path in a full path. Okay, so you can see that that's the data. So that's prefetch. So prefetch is pretty useful. It is actually, yeah, you can search for known binaries. These are especially suspicious ones. that are used commonly for lateral movement, things like that. And we talked about the timeline. It's more useful for doing this particular artifact is more useful for the timelines. And here, this slide just shows us the you know, the runtimes are, you know, kind of an array here, and yeah, and you can just filter that. You can actually, as we've seen before, you can create your own artifact based on an existing artifact. So you can call that and filter the results, you know, based on file name and, you know, things like that. All right, so so that was Prefetch, and there's a whole bunch of similar ones here that are skipped, and you can have a look at that later. But you know, they're all the different ones. Can Velociraptor Prefetch Parser return created date of prefetch file as first execution? So yeah, that's a good point, right? Because again, the times are actually the times are actually that's when the file was first birthed, like the creation time is the first execution of that binary, right? So you actually have the 8 timestamps in the file, plus the file, the actual file itself has timestamps as well, right? Including the creation time, and that should be the very first one, right? So that's part of the artifact, but I think there's a bug in here that's been fixed. I think this is not working correctly. We can fix it real quick. We can. So this is one of the interesting things about Velociraptor, is because it's all just an artifact. Then you know, we can basically go and change it and you know, and improve it. So the timestamps, right? So this is the timestamp here. So that's the birth time, is the creation time. So that's exactly that question, right? So you can, and then if we save that and we just collect our custom one, yep. Then I think there was a slight, yeah. So it didn't. Now it carries it across, right? So this has the timestamps here, but this looks a bit early. I think that is the time stamped version, right? So when you unpack something, that creation time. No, that doesn't look right. 2019. I don't think that's that old, this VM. Oh, it might be. I don't know. So yeah, I mean, that's another data point there. Cool. Yeah, so it's basically the rest of the artifacts here. I just want to kind of rush through them a little bit, because they're very useful, right? But they're not super interesting from a Velociraptor perspective. They're just different ones. You know, you collect this one and you get results, right? Like, so for example, like the BAM stuff, right? It's just a background activity moderator. So you can basically see it's just a registry key, and it parses it, and Velociraptor will just parse it for you and tell you a little bit about it. So each of those artifacts tell you something slightly different. You know, like if we could just collect the BAM, and you know, and we just take a look, and that's it, right? So it just sort of shows you, okay, this is the user, the I user. This is the downloaded VM for testing from Microsoft. So again, you know, we basically have, you know, this binary. This is the seed, and you know, the execution time. So this is that, you know, one kind of evidence, and they're all basically just based around evidence of execution. So you know, it tells you when something executed, and so on. And then this is the SRUM, which is in another one. So that's an ESE database that's stored in a particular place. and there is, more information about it, but, effectively, again, it just tells us different things about the system. So I kind of skipping this so that we don't run out of time. But I always find that part, it's important, but it's just kind of a little bit boring because you just select the artifact, click a button, and then you have it, right? So it's not super exciting. So I'm just going to move on to the next one. And the next topic is the Windows event logs. And that's actually a really common, basically it's one of the most used sources of information, event logs. But a lot of people don't really understand how event logs work, or don't really appreciate how the event logs work. And so I thought that I'll talk about this a little bit here, just to give you guys a bit of an understanding of how event logs work, and then the problems that you can have with doing forensic analysis of event logs. So just as a quick recap, the event logs are stored, they have an extension of Evtx, and they're stored in this directory. So they're just files that contain the event logs. Now, if you're familiar with something like syslog from a Unix system, then the event logs on Windows are a little bit different. The first difference is that they are a binary format, right? Whereas a syslog is just a text format that has lines. So because it's a binary format, it's really designed for several like these features. It's actually kind of a clever format. The file itself has a rollover mechanism, so it overwrites itself when it goes. It goes to the end, and then it starts to overwrite itself on the beginning, right? And so a rollover is built into the file format. It's also in binary, which means that it's actually XML, but it's encoded as a binary XML. So you have to parse it, with a tool, because you can't really read it. It provides some kind of compression, but it's not really compressed. It's compressed in the sense that the XML tags are compressed, but the data itself is not really compressed. But the best thing about this file format is that it's a structured file format. So from a forensic perspective, event logs are kind of a pain. They're not really as useful as syslog. For example, like in a lot of the Unix type, the Linux type investigations that we do, even if the syslog event logs are rolled over, they're just deleted, and it's possible to carve them out of the disk. So in some cases, we've been able to carve logs out of disks for years almost, right? Since the incident, so we can go back quite a long way depending on luck, right? But with event logs, it's difficult because of this rollover, because it actually overwrites the same file again and again. So you can't really carve it as well. Because it's binary, then it's also a little bit harder to carve. But having structured records is actually really good. So let's have a look at what it looks like. We can just parse it. So this one just parses it, in the command line, but we can just parse it here. So let's start our create a new cell, and okay, and then just select star from. Now it's just a parse, so we're parsing. So all of the parses start with parse underscore, and we're just going to parse an Evtx file. So what parameters does it take? The file name, okay, and it's going to be C Windows System 32. I'm just going to use / because it's just a little bit easier. Right, so win evt logs system evtx, right? So win evt logs system .evtx. So that's the system log, but let me just limit it to, I don't know, 10 messages, so not too many. And you'll see that it basically starts parsing the file. I cannot just write system as abbreviated path to the system Evtx. No, so it's actually you actually need to give it the full file that it parses, because it is just a file parser. So it opens the file and parses it. So there's no shortcuts here, and we'll see later on that there's actually quite a lot of different log files in the log file directory, and they're all different, right? So yeah, so this, but again, it's not really a big problem because the artifact will hold the right path here. Let me just have a look at the raw data, and you'll see that we have the 3 columns. So I'm just going to show you, fold them out. So this is one row here. And so we have the 3 columns. It has a system column, then we have a user data, and then some of them, and then we have the message, right? But some of them also have event data as well as user data. So they're basically slightly different, right? But they're just additional data. But the nice thing about it is that it's actually structured. So the system, so they come from Evtx, they come from XML, right? But they're parsed into JSON. So there's one JSON type structure here, and then and that's the system one. So the systems column, if you like, is that has a constant structure. So that structure doesn't change. But the user data column, it can be anything, right? Depends on the event log type. And then we have the message here. So let's look at some of the interesting fields that we can see in the data. So in the system data, in the system column, we have something called a provider. A provider is just the kind of program that provides these kinds of event logs, right? So it tells us where the event logs come from. So it's a GUID, which is a unique identifier for the piece of code that will generate these kind of events. And then we have an event ID here. The event ID is essentially the type of the event, different types of the event. Then we have various other things, and then the time created. So this is the system time. It's a Unix epoch time of when this event was generated. Then we got the event record ID, which is just a number that keeps going up. So it's just the total number of events in this log file. So remember that the log file doesn't start with, it would originally start with event record ID of 1, but then when it gets to the end of the file, it wraps around, and then the beginning starts, it keeps going, that number keeps going up. So the file can start with a higher number, right? Because it just wraps, it wraps around. Then we have the channel and the computer. So the channel is essentially the name of the log file, right? So this is the system event log. So the channel is system, and this is the name of the computer. So that is in the system column. Now, and then we have a user data. User data is another column which has application-specific blob of structured data. So if we have a look at this particular event, it says log cleared, right? So this event says this log file was cleared. And then in the user data, we're going to get some context about who cleared it, how did they do that, and these kind of things. So we actually have some context here. All right. So now let's have a look at the event message. Now in here we can see that there is an event message which tells us what it is. There's log file was cleared. This one says the start type of the bit service was changed, from this to that. and so on, right? So there's different system uptime is whatever. These are just different messages. But the message here, the string here, start type, that is actually not in the event log file at all. So that's kind of an interesting thing. Let me just show you the event viewer. So we'll start the event viewer. Now, inside of the Evtx file, we don't actually have, let's have a look. Okay, so we don't actually have the message is not encoded in the event log files. This is very different from syslog. So in syslog, essentially it's a text file and it's a text message. So the full message, all the information is in the syslog file. But in a Windows event log, it's not. What we actually have is that message is omitted. It's not present in the event log file. So if we have a look at, so Velociraptor actually just makes that available here for us because it's parsing it, but the event log itself does not have that. Let me show you, here's an example. So over here, we can see that the general tab has the message, which says, whatever it is, right? But the details, that shows us the XML record itself. So it's basically the same thing as what we're seeing with Velociraptor, but you see that message is not present. But what you can see is that event data here, you can recognize it in this message, but it's not exactly the same. Like the access history in Hive, and then it has the name of the Hive. So that name of the Hive is actually what's, given here, right? But the actual message of the access history is not present. So why would Microsoft do that? Why would they hide the information? So it turns out that because we are not storing the actual message in the Evtx file, it allows us to do things like internationalize the event, right? So we can have the text of the event in different languages, and then we can have the UI display different messages for the same event. So for instance, in Windows, if I had a different language pack loaded, then when I can view the very same event log file, and it would have a different explanation here in the right language, in the correct language, right? So that seems like a reasonable thing to do. And it's also saves some space in the Evtx file because you don't have those messages in the file. But so it seems reasonable, but in reality, it's just a real pain, right? Because what it means is that if you're trying to do forensic analysis and you just get the Evtx files, you just collect the files, then you have a problem because you have no idea what those messages are. So we'll look at that problem in a minute. But I just wanted to show you here a screenshot of, this is a Chinese system. And what I'm looking at now is a message, one of the event messages that basically says that the Windows installer installed Velociraptor, right? So we created this new service. But as you can see, this is the event data that's in the event log. So this is just the different kinds of information, and it's being interpolated into the message. But the message itself is in Chinese, right? And then this data is interpolated into the message. So it's being internationalized, the same message, right? Right. So this is the same thing, right? You've basically got some additional data, and then this is in English, right? So you have, so this sentence here, special privileges assigned to new log. So this is an interesting thing, right? When you look at any kind of message in the event log, any message at all, then all you are seeing is this event ID. That's really what's stored in the event log. That message is not present. So sometimes it's very hard to tell what happens, right? So if we go and collect the Evtx files from all the endpoints just as files, and then we try and look at them offline, then really all we're going to see is an event ID, right? So we see an event ID, and then we just don't know what it means because we don't have that context. That message doesn't appear. So if it's a very common event ID, like see, this is 4672, so maybe we can put it into Google, and there are websites out there that keep track of the different event IDs and they tell you what they mean. That works for very, very commonly used event IDs, but it doesn't work a lot of the time, right? Because you just don't have that information. So what is going on? How does the event ID affect the message? Where do we get that message from? And so it turns out that the way this works is that there is a mechanism for resolving the messages from the event logs. And the way it works is you basically look at the channel and provider, which remember are the two elements here, right? So that's the provider, right, which is the GUID here. And then you have the channel here. So they're in the system part of the event log. And then you put them together, you build a registry key like that. And then inside of this key, there's going to be a value called event message file, which is a path to a DLL. Then you open the DLL, then in that DLL, you're going to have a resource section, and then there's a message table, which is just some kind of, essentially it's a part of a resource of a PE file, which is like a big table of strings. And in that string, the index into that is really the event ID. So so when we see here that it says, event ID 4672, what does that mean? Well, that 4672 is an index into a table of strings, right? So there's nothing really magical about this number. It's just an index, right? And it just so happened that most of the time they start at 4096 or OX1000, and then just keep going up. And so that means that those numbers are not actually unique or special or anything, right? They're not really unique. That number can be reused by a different provider. It's just an index into a table. And so that number there's nothing special about it. And this is where it becomes very complicated, because a lot of the time you'll get an event ID and you can search for it on Google, and it would be completely irrelevant because it's something completely different, because a different program is using it. So that makes it even harder, because even those hits that you might get, they are actually not relevant. Because, so let me just show you again with a picture how that looks like. So the event viewer basically looks at the Evtx file. It looks at these pieces of data from the parsed record, and then it opens the key in the registry to get the event message file, right? And then it becomes a little bit more complicated than that, because there are MUI DLLs, which are internationalized version of the DLL. And so we open that DLL and then extract the message table from that. And that gives us a string with expansion directives like %1, %2, etc. And then we use the user data section to interpolate into that. So it's actually quite complicated to get those messages out. Velociraptor can do that because Velociraptor is running on that system. So because we are on the system, we can emulate that process, and we can go ahead and look at the registry, pull out the files, and look at the files, and then pull out the messages. So that's why when Velociraptor parses the Evtx, like we're doing here, it always appends the message to the record, and it interpolates that user data into the message if possible, if it needs to. So so that's why we've got the message, right? But if we just collected the files, like just bulk files, like for example using the Cape files target or something like that, then we wouldn't be able to resolve it off the system, right? We have to be on the system, because in order to resolve the message, we have to look at the registry and the DLLs on that system, right? So unless you're taking all the DLLs, or you're collecting all the files with all the possible DLLs plus the registry hubs, it's very hard to put these things back together. Question: are these DLLs included in the Cape Triage artifacts? No, so they're just DLLs, right? They're not included in any of the artifacts, because they're just DLLs on the disk, right? So usually when you're just collecting event files, and they're not stored in the same directory, they are actually stored all over the place, right? They're basically stored together with the installation. So some will be in program files. It's part of the application, right? They're just, the DLLs are part of the application. So when you're collecting the Evtx files and you forget to collect the DLLs, then you come to analyze it, then you have a problem. I mean, if you're looking at very commonly used ones, then that's not a problem. But there are some, there are some very unique, very specific kind of applications. Okay, sorry, I've got a few questions on Q&A. Let me just catch up. Sorry, I've missed those. Can we use grape alloc command here and before parsing Evtx, or is it possible to do post parsing? Okay, that's a great question. So what we're asking you is, can we so can we extract the message before parsing the Evtx? So what we're trying to do, that's actually the next slide here, is we're trying to build like some kind of a database of these event IDs and messages, so that we can have some kind of machine way of resolving those things together. It's not the best, because again, sometimes there are some unique programs, like unique applications, and they are not they're not included, right? So it's, again, like we try to do things like have let's say Windows Server 2019, and then we go through and just dump out all the messages into a big SQLite database. So there is this project here that we try and do here, this Evtx data, and that's what we try to do. And that works a little bit, because at least it gets all the standard software. But if someone has like Office or Outlook or Adobe or any of the any application really, then we won't be able to know that. There's another question. Like, we want to check for certain event IDs before parsing and then display the list with those event IDs. So it's always possible to look for specific event IDs, right? It's just the message that's difficult, right? So it's always better to parse it on the endpoint with Velociraptor rather than bring the files over. I guess this is kind of the take-home message from this part of the session, is that you're always better off to just grab to parse all the event logs on the endpoint completely, and then and then pass the parse result back, than just grab the files. Okay, another question. Does Windows Event Forwarding take care of this automatically, including full event messages, info in events? I don't think so. So I don't think the Windows Event Forwarding itself includes the messages, the full messages, right? It just passes the same thing, the Evtx files. So again, vanilla Windows Event Forwarding probably has the same idea. But I think things like the Elastic, the Elastic Win file bits, they do also enrich with the messages, and I think Splunk does as well. So it's a common problem, right, in the field, right? So it's just something to be aware of. So generally, event forwarders would put the messages in there as well, right? Another question: can we parse same Evtx from all VSS? Yes, so we can do that. I'll show you in just a second. Okay, we have another question. without affect performance to collect the extra event name parameter from registry while collecting the event logs. I don't think so. Well, we're not really that's not when we collect the event logs. We actually parse the events, and that's when we check the registry. I think it's just it's pretty quick. It just resolves the message out. So it's pretty quick. I don't think it affects performance too much to parse the messages, but maybe we'll have to check if there is a performance issues. Can the GUID be parsed offline in analysis machine to translate the event name from the event ID? Okay, that's right. So this is a good question, right? This is so this is what this project here is trying to do here, this Evtx data. If you go there, then you'll see that we tried to sort of create these kind of resource that we could use. And these things here are all IC.db. They are SQLite files with the mapping between event IDs and messages. So using this and then using this tool, dump Evtx. So dump Evtx is like a standalone tool that uses the same library as Velociraptor, but it then builds those SQLite databases by just essentially dumping all the messages from all the event logs. You know, essentially it just looks at the registry and pulls out all the providers and then builds a database file, SQLite database. And then you can use that database to resolve files. You know, so if you end up in a situation where you just have Evtx files, but you don't have, you know, you just get given these files, right? So you don't have any ability to go back and check the DLLs and so on, then at least with this dump Evtx, you can create a SQLite database, right? Which can, you know, help in resolving them. But again, this can only work if you have the program installed that generated this thing, right? So, you know, if it's a particularly unique software, then it won't work so well. Yeah. The other thing that I wanted to show you guys here is the Evtx attack samples database, which is a GitHub resource, which, you know, actually contains a whole bunch of Evtx files generated by different kinds of attacks that happen in the attack metrics. So these guys basically replicate these attacks, and they're generating a lot of the event logs. And this is really useful when you want to look back and see what kind of signature something, you know, leaves in the event logs. And because you got to remember that the current state of the industry is very, very, very event log focused, right? So a lot of detection is really around event logs, because for things like Splunk uploads and, you know, and Elk Stack, you really can only see the event logs. You can't see, unlike in Velociraptor where you can go and actually look at many different types of artifacts live. You can't really do that in a lot of the existing technologies. So you've really got to have these event logs, you know, enabled, and you're really just working off event logs for most of your visibility. So this is a good project to take a look at as well. And it's a good source of event logs. So yeah, I mean, yeah, this is a bit of an exercise to show you how to use that standalone command line tool from there, if you ever need to be in that situation. Yeah, and then some references here. So yeah, so out of this interesting, you know, the main thing that you should get out of this exercise is don't just collect the event logs blindly, because then you'll have an issue. I just wanted to quickly show you guys what I tend to do in an investigation. And you can, you know, it's always better to parse the event logs rather than collect it. So let me just show you an example of this very cool artifact called Evtx Hunter. So if I just search for Hunter, this is the Evtx Hunter. And this basically started off as an exercise when we were doing a particular DFIR task where there was lateral movement. So essentially something like domain user credentials were compromised, and then that domain user, was used to essentially, laterally move across the network. So this is a pretty common type of, of investigation. And in this case, the domain credentials were pretty unique, like there was a unique name. And so we could essentially hunt for it in the event logs. So we had no idea what this user was doing across the network. We just knew that this account was suspicious. So pretty much we wanted to know what this account did anywhere at all, right? So you can using the traditional approach, you can look at specific event IDs. You can say, okay, was it a log on, log off event or whatever, right? But it turns out that there are basically event logs related to anything, right? Like literally any kind of service or any kind of provider or anything really that might also mention that username. So for instance, so we can create, like say Mike, we can search for Mike, and then essentially and here is where we can add the VSS, right? So we can look at different VSS versions. There was a question before about that. But what this does, let me just launch it, is it basically goes through and it parses all the events. So it parses them completely, right? So it doesn't necessarily, so it's not just looking at the file, and then it creates a string out of the event, and then it matches that string. So it's really dumb. It's like carving in Evtx file, basically, right? So it's carving all the events that happen to have, that username in it. So what we're going to get out of this essentially is any kind of interaction or activity that just happens to mention that username, whether they used bits admin or whether they used, Chrome update or anything, like really. And that worked so well because it gave us a really good idea as to what that user was doing. Okay, we have a question. Does Evtx Hunter handle event logs not stored in their standard locations? Sometimes we store Sysmon logs on different volume with more disk space. So you can see that it actually takes a parameter. So it takes a parameter of where to glob for the Evtx file. So you can change that if you needed to, but that's the default, right? So yeah, I mean, all it does is we can look at the the whole reason we're doing this course is so that you can see the event logs and you can see the query and it can understand the VQL now, right? So you can see what it's doing, right? It's basically it's doing a glob of all the Evtx files. You can, we can restrict it to specific files, if we needed to, right? So there's the path regex is the parameter. So we don't have to hunt everything if we didn't want to. And then we can do a VSS type of comparisons. So we can see if there's any differences between the versions of the VSS. And then, we basically just parse the thing out and extract all the fields that we want. And then we create a string using the format. We just kind of like put all the strings together and then we match it with the regular expression. So it's pretty dumb, right? And so if that name Mike happens to be, anywhere in there, then it's gonna return it, right? So it's pretty simple, but it works really well, right? So we're getting, all kinds of unrelated stuff. But it gives us like, essentially we're going fishing. We're just trying to catch anything to do with, anything, right? Yeah. So yeah, it is a pretty effective one. See, for example, here we've got compatibility fixed applied to .NET, you know, and that happens, you know, when someone runs something to do with .NET, I assume. I'm not really sure, you know, but there's a different provider there. So, you know, if the user logged in and started to run PowerShell stuff and something happened, you know, and it upgraded something, then, you know, that could be an evidence of them running something, right? So this works really well when the domain admin that was compromised is not very active and they're not really doing stuff. Like, you know, a lot of the time that's what happens, right? There's a forgotten domain user that no one remembers, and there's a weak password, and then it gets compromised, and then, you know, that moves around. So basically, we're interested to know whenever anything happens. All right, so that's cool. Yeah, it could take a long time as well because it parses everything, right? It brings out. There's a lot of log files that are not super relevant, and they probably won't have any hits. See, so there's some descriptions, bits. So that's the bits client, for example. Right? All right. So yeah, let's have a look at more of the event log stuff. Yeah, typically while investigating Evtx, we convert to CSV or text and then perform searches. Yeah, it's basically the same thing, except we're doing that on the endpoints. So we're just getting back the relevant stuff. Okay, cool. So it turns out that you can actually enable and disable event logs. So over here, this is the event viewer. And if we have a look at the specific providers here, so these are different event log files, but they're just different channels, actually. And so you can see that this is like a file. I'm just picking one at random. You know, we just pick one randomly. And you can actually see these are actually different files. If we look at the properties tab, so over here, then you can see the file name of each of those is like Microsoft Windows BitLocker. So it's basically the path, you know, except that instead of a slash, there's a %, you know, 4B. So it's kind of URL encoded, but that corresponds to the Evtx file, and, you know, it just shows it like that in the UI. It turns out that we can actually disable these things. So we can just right-click, enable log or disable log. So this one's already disabled, but let's pick one that's enabled. So I don't know. I mean, like terminal services, right? So here's a terminal services one. Right-click, disable log. So what did I just do, right? I just disabled the log. It turns out that actually disables the log, like it really does, right? So surprising, but that's how easy it is to disable logging. You just right-click, disable the log, right? So an attacker can just do that, right? You can just disable the log, and then when you use the terminal services, none of these logs are going to work. So when you have a detection solution that that depends on collecting logs, and you can just disable the log, that's a problem, right? So it turns out that when you actually do this, then you can actually see what happens when you do that by looking at a procmon. And you can see that it ends up setting a registry key here in this this key. So like down here, right? So we can look at it with regedit. And you can turn these logs on and off, right, by just setting this enabled key, right? So this is where this is actually kind of an interesting detection, because what we want to do is we want to be able to say, well, you know, is this log disabled or enabled on particular machines, right? Because, you know, that could be a red flag, or it could be a problem that we don't have visibility of logging. So let me just quickly have a look at it. So HKey, local machine, software, right? Microsoft Windows, current version, Win EVT, no, Win. Win EVT, there it is. Channels. And then these are all the different logs, right? So there are different channels which basically correspond to the different log files. So remember, the channel is the same as the log file. And then there's an enabled bit here, right? Which is just a value inside of each thing, right? So we could actually detect these kind of behavior just by writing some VQL, right? So we could jump into here, create a notebook, and say 2, and then just maybe write a quick artifact to detect these kind of things. So in this one we're looking for a key, a value. So we're just going to glob the registry. So the same thing as what we've done last time. And I'm just going to use 3 dashes because it's got backslashes in it. And backslash enabled. Right? And then the accessor is going to be registry. And then this one, you see this is actually the name of the log, right? So I'm going to just do a star there because I want to see all the logs, right? So, and then limit, I don't know, 50, let's say, for just to see. And you can see that we found some of them are enabled, right? And this goes back to, by the way, you can see that they have a slash in it. So Velociraptor adds the quotes in there to keep that component together, right? It's one component. It just happens to have a slash in the name of it, but it's just the one key. So I think we talked about that in a previous I think the previous part, right? Last time. So you can see then, and then we have the data, right? So let's bring that full path, and then if we look here, remember that this is the data column. We have data.value, right? So data.value, and that's going to be either enabled or not, right? So this is going to be either 1 for enabled, 0 for not enabled, right? So then from here, it's easy. We just get the directory, do your name, path equals full path. So that gives us the directory because it's got enabled on the end. That will strip that enabled part off and just give us the directory part, right? So just do that. So that's this last part. And what we want to do is we just want that last part, right? So what we're going to do is base name. Base name is a function that just gives us that last part of the path. So, it's just going to give us that last bit. So essentially, that's the name of the log file, right? So then we can say, as channel. That's the name of that log file. So yeah, so basically, that just says if it's enabled or disabled. So this is another example of how we can just go from an idea. It's like this is basically what I did here, right? I realized that you can just right click the log and you can go disable log and like, hey, what does that do? figured out the registry path that is set as a result of that, and and then I just go and create an artifact straight away, so I can now hunt for it. Okay, quick question: why 3 dashes we used? Okay, so if you recall, we've discussed the types of strings that we can have in Velociraptor. So if you're using just normal quotes, then those backslashes, they're escapes. They become escapes, right? So then we have to double them all the time, right? So it's kind of more tedious. We can do that. We can just, so it's the same thing, right? But we have to double them because otherwise they become like an escape. So you might say it's more readable to not double it. So so if we use 3 quotes, that's a row string. Row strings don't have escapes, right? So we don't need to double it. So I mean, this is the same thing, right? Yeah. So it's just a matter of choice. Yeah. Okay. So and then we're using the access to registry, which means that we can glob in the registry. So yeah. So so we can convert that into an artifact pretty easily, and then we can hunt for it everywhere, right? So we can just search for when it's enabled or not. But you can see that a lot of them are actually not enabled. Some of them are enabled, right? But a lot of them are not really enabled by default. So we don't really know whether they're supposed to be enabled or not. But we might be able to do some stacking. Would it be okay? There's a question. Would it make sense to somehow compare the enabled to what is default to find the outliers? But that's an excellent question. We don't really necessarily know what's default. I guess it depends on also group policy and things like that. But we can do stacking. When we do stacking, then we can say whether something is makes sense or not. So I actually wrote this artifact here, and we can do a hunt. And we can do like disabled logs. Oops. And I think it's this one. So this artifact looks for modifications to the event logs, and it actually has 2 providers. So this is what we did now, which is basically the same thing, right? Looking at the time of modification, and and then basically we're looking at this key just as we did, but it's a slightly different one. And then this second one, there is also another place that that you can disable the event log as well. So there's there's more research that went into this, and you can actually disable it in a couple of places. So there's one, you can disable the channel, which is what we've seen, or you can also disable a provider. There is a blog post that explains it in much more detail, but for the sake of this, we just click launch. We just essentially look for the defaults, right? And when we run it, I mean, there's only one machine here, but then you'll be able to see, you'll be able to stack it, right? So if you have multiple machines here, then when you do this, then you can just do a group by and account to see which one's enabled and which one's not. So for example, here, we would do a group by, and what we want to group by is the channel name, right, with the fact that it's enabled. So when we have a comma here, then it looks at pairs, unique pairs that are unique, right? And each unique pair like that creates a group, makes a group, right? So then when we do a count as count, then it will count how many are in each group. I mean, there's going to be just one here, but basically what you'll see here, when you have, this is called stacking, right? When you have a bunch of machines that are all the same, then, then the count will be high, like for, it will be very high for machines that are all the same. because they have the same setting, like this channel analytics, say, and it's, enabled is 0. And let's say we had 3,000 machines that had analytics and enabled was 0, right? But then if we only had 1 or 2 machines that had analytics and it was 1, then they are outliers. So this goes back to the outliers. So this is how you would essentially detect outliers. Another question, can we modify system settings with VQL queries? Enable logging for some channels. Yeah, so we're going to see that in session 7, remediation, when we can do remediation to actually fix the state of the system towards a particular state, right? So if we decide that, hey, we want to enable a particular log, then we can do that through a hunt. We'll see that in 7. Okay, so this was a cute little exercise just to show you how to do, again, hunting. Again, this is what I was getting at the last time. A lot of the time, most of these artifacts are around, just doing some globs, just searching for, the right thing. So, just a quick glob, quick filtering, and then you'll actually get some pretty actionable data. Okay, so that was the exercise here, and this is another way. By the way, so read reg key, we just did a glob. Read reg key is very similar to glob, but what this is used for is just to make it more convenient, because when you have a registry key, like any registry key, then typically what happens is there's a key here, and then you have a bunch of values, right, inside of this key. Now, if we just do a glob, remember that the key looks like a directory, and then the values are like a file inside of that, right? So we can do a glob like we just did, */enabled, and that's fine. But then if you want to, but then that just has one row and just for the one value. What you ideally want to have is these are all on separate columns, so that you can have one column called channel access and have that value, one column called enabled and have that value. So you want to split them up into columns. And that's what read reg key does. You give it a registry key, and then it basically splits all of these into separate columns so that you could, manipulate them. So let me just see if we can fix that. Like this. So in this case, it sort of doesn't matter because it's just got the one, the one enabled. We only really care about enabled. But if we just did this, read reg key, this, then it would just split them by just. Oh, and it's not globs. It's called. Oh no, it is globs. Globs. Then it should split them by. And then we have to do a star. Select star. So it just sort of splits them off into separate columns. So that's the key, and then we've got all of the fields are separate columns. So it's a little bit easier to kind of compare different values within the same key. So that's the main difference between the two versions. All right, cool. So let's move on to event tracing for Windows. So that's ETW. And I'm just going to really quickly cover ETW, but ETW is a super powerful feature. And there's really a lot of detections that we can do with ETW. So ETW is event tracing for Windows. And that is really the way that Windows uses to basically trace for certain events that happen in Windows. And in fact, the event log architecture is built around ETW. So ETW is like the engine that makes the event logs work, right? So event logs are part of ETW. It's not really very different. So in Velociraptor, we can just hook into the different ETW providers. And this is just a quick overview of how it works. So imagine that there are providers, ETW providers. So they're basically pieces of code that can provide events. And then there are ETW consumers, which are programs that are interested in certain events. So the way it works is the providers advertise that they can provide certain events, and then consumers register interest in that event. And when that happens, then Windows kind of connects the providers and consumers together, and then passes the events directly. So you see here, it's passing it directly to the consumer, or you can go through a trace file. So you can trace through a file if you want, or you can trace directly. In Velociraptor, when we use the ETW, we trace directly, so we don't need to go through a file. We just trace directly. All right. So let me show you how the providers work. So essentially, providers just register that they can provide stuff. You can tell which providers are which by running this command, logman query providers. Let me just start up another shell. Okay. And when you run this logman query providers, it takes a little while, but it basically just kind of prints out all the providers that are registered with ETW to provide, data. Come on, it's a little bit slow. Yeah. So you can see, just stop it here. So over here is the name of the provider. So each provider has a name, and then here there is a GUID. Now this name just basically says it's just a user name, right? It's a user readable name, but it basically tells you the piece of code that will, the kind of information that it might provide. But really, the GUID is the thing that means something to the system. The name doesn't mean a whole lot. And as far as Velociraptor is concerned, it's you can see that a lot of them are actually kind of really interesting, and they sound really interesting. Like this is a TCP OP, this is a task scheduler. So maybe that will give us events about when tasks are scheduled or descheduled or added, removed, these kind of things. There's all kinds of interesting stuff here. And so an event will be just immediate whenever something happens on this provider. Are the GUIDs unique to machines, or are they universal? Well, that's an excellent question. So it's unique to the program, right, and universal. So it's just unique to that provider. So it doesn't change, and it doesn't change between versions of that program. It's always the same. Yeah. So it's not unique to the machine. It's unique everywhere to the same program. So that means that it's just an alternative to the name, but it's more precise than the name, right? So like this one is WebAuth. Let's find something that's kind of fun. I don't know. We'll just pick something random, like WinHTTP or WinINet or something like this, right? WinHTTP. So what we do is we take this GUID, right, for this, and then all we do is we just select star from. Now, ETW is an event thing, right? So it's going to be a watch, because watch is for events, right? And we just watch ETW, right? Question mark. And then we provide the GUID, right? So we just paste the GUID in there, right? And I actually don't know, what it's going to do, but let's see. I think that was the HTTP, win HTTP, right? So usually if we start Edge, so it depends on the program that will actually, generate these events. Usually with Microsoft's tools, they tend to do that. They tend to generate these events. So I think for URLs, not sure if, yeah, so we've got something already. I just wanted to generate some traffic. So we've got something. So I don't even know what these things are. Work item, wait callback. So these are just different kinds of events that are generated. Actually, I think if I'm looking at, there's a URL one, win inet. I think it's this one maybe. So some of them are very low level. So they're not super useful because they don't give a lot of information, but some of them are very useful, right? So let's see, maybe this one. So I think we actually have, I don't know what the thing is. Get rid of that. Just generate some traffic. And then I think some of them will generate URLs. I forget which one it is. There is an exercise. We'll just do that. I'm just going to go along with that. So DNS clients, this is the one we're doing for the exercise, right? So there's the DNS client, and this is the one that we're doing for this exercise. But you can just explore, the different GUIDs, just see what happens. A lot of them are not very documented, but you can just see what kind of events it provides. Let me just stop that. So let's see this DNS one. So this is so in this command, we are getting more information about this provider, the DNS one. So in this one, this is the GUID. Okay, that's great. So we can immediately just go in here and use that GUID. Right. So there. And then it turns out that there is a thing called the keywords. Right? The keywords are basically the type of events that it generates, right? So it's like it allows you to do sort of like a search, a filter for the different events, and these are the different values. So you can specifically look for specific events here if you wanted to, and then we have levels, the error, warning, and information. So they're like log levels basically, and over here it tells us all the programs that are currently configured to produce these events. So that these are just the different PIDs, right, that are currently hooked into the system to produce these events, right? So if we wanted to, so if we just, in this case, we can simply look at the whole thing. So just do this, and this will generate DNS, packets, right? So we'll just generate some traffic here. I don't know, and hopefully this will generate some DNS activity because we are in a DNS provider. So let's stop this. Right, and there's all kinds of events, right? So there are some, so this is a query, right? So the DNS query is going out, right? And then some of them have answers, right? So this is the server address, the query name, and then some of them have, so this is very similar to the event logs, right? Over here, that's the event ID basically, right? The event ID. And then basically that just gives us, the query name. So if we wanted to, we would simply, so let's say 3006, that's the event type. So just like event ID, and we would just do where system dot ID equals, oops, which is the interesting ones, 3000 and 3006, I think it was. So test query results. Yeah, I mean, so you can basically just pick. I'm not sure which is which. We still have to do some experimenting to find out what is the best event ID. But if we do this one, right, then it will filter out, only certain types of events that are more interesting for us. So if we wanted to, generate like, I don't know, yeah, Amazon or something, and then, okay, and then over here, okay, then we've got the query name. And so we need to know like what the query is, and in some of them we can actually get results. So, oops. So in here, what I want to show perhaps is the system.timestamp, right? And then here, event data dot query name. So that's the DNS query, and then this is the time. So this other information, it's maybe not that interesting. So now we're just getting an event. And so whenever a DNS query is performed, if we're going, somehow to, any of these traffic is generated, then we should be able to see the queries coming in, right? So the queries are coming in. So that is now an event query. And we talked about event queries really quickly in the second module at the end. And we talked about how we can use that to create some kind of detections. So we can simply do that by essentially converting this into an artifact, right? So we can create a Windows ETW DNS monitoring, for example. And then we just paste our artifact here. And it's going to be a client event. So that's the type of artifact. It's going to be on Windows, right? And we don't necessarily have any parameters here, so that's fine. And we can leave the description or not. Doesn't really matter too much. So that now becomes a monitoring artifact, right? So when we save this, save it, then we'll have a custom artifact that monitors the DNS, this one. So what we're going to do is we can install it into the event tables. We'll go to the client events, and then we take a look at the current client events, and we've got this one is the default one, which tells us the telemetry from the client, like CPU usage and these kind of things. So we just go over here. We can target by label. So we can say, so this allows us to say, okay, all the machines on the network will run this event monitoring query, or we can target by label to say only these machines will run this monitoring query. So we can be much more specific. But I'm just going to run it on all the machines and just add that monitoring to it. So once I click launch, then all the endpoints will start monitoring for this. And so let's refresh that. So you can see that it's immediately shows up. Now I remember that I'm still in that user context. So it's each machine is forwarding its events to the server. And there's going to be a little bit of batching going on here. And as I'm generating new DNS, right, like I don't know, like create maybe eBay, whatever, right? So generate some traffic, and then when I look at it here, just kind of refresh it, then I should see data. This is the logs. So the query logs, the query is running on the endpoint, and therefore it has logs. So I can see the query logs this way. And then the raw data is the actual DNS hits. So there's going to be a little bit of a delay. I'll just leave that a couple of minutes until it syncs. Okay, cool. So we'll revisit that in just a minute. I don't know how long it's going to take. Yeah, we'll come back, but it should hopefully just start to feed in those DNS results in. Just check. Yeah, I mean, I think that should be right. All right, let's go back to this. So we covered ETW. So the other thing that's actually pretty cool is that ETW, because it's the thing that is backing or implementing the event logs, it turns out that it's the same thing, right? This, when you go to any event log, just pick up system, for example, whatever, and then you look at the provider here, that is the same thing. It's the same provider, right? So you can actually, as we've seen before, we can do watch Evtx, which literally watches the event log file itself, right? For when the new records are written to the file. But that is a little bit less efficient than doing the ETW, watch ETW on the same provider, because that will actually show us the same results. So it will show us the same events, and it will be faster because it doesn't need to hit the file for us to see it. Yeah. Okay. So see if there's any refresh these things. Yeah. So now we've got some DNS coming through, right? So that's the DNS thing that we've done here, and we can see the query and the times. So you can use that to monitor for DNS on the endpoints. The other cool thing that we could do is you can also use Sysmon, right? So Sysmon. So this is an example of Sysmon, and it goes back to essentially the watch ETW and watch Evtx, the difference to that I was just saying, right? So this artifact will install Sysmon, and as you know, Sysmon usually writes events into the log file. But what we're doing here is we're actually watching the ETW provider, not just the log file. So when I launch this, it's going to actually go ahead and install Sysmon on the endpoint, and we're going to start to monitor results from that. So where is it? Oh, sorry. This one. So by default, as you know, the Sysmon writes to the log file, but we don't have to do that because remember, we can actually disable it. So, if we go in here, Microsoft, where's Sysmon? Sysmon. If we disable that, where is it? Oops. One of these things. Then even if we disable that, then it will actually still work because ETW is still working underneath. So even if the log file service stops receiving those events, it's still, Velociraptor will still get them through ETW. So that's why this this artifact is using ETW because it's more reliable. Oops, Sysmon. It's more reliable than because it's using that GUID. rather than the event log file itself. Even if we disable it, it still works. Yeah, and I think we're going to get these events soon. All right, so yeah, so question, what is the best way to identify inefficient client event that consume RAM, CPU more than expected? Well, that's a good question. I mean, I guess you can turn them on and off to see whether they change the and we have a telemetry, right? So we can collect the generic client stats, and if you click on reports, then you can see the telemetry here, which is how much CPU we're using. So if you keep an eye on that, then you can see what the total CPU usage is. But it's difficult to tell what each kind of thread was doing. Except that I guess what you can do is you can have a look at the logs, and you can see in the logs, you'll get a query stats. So that's what each query is doing. So for example, it's difficult to tell exactly how much CPU each query is using, but you can tell like how many rows it's looked at, and how much data it's sent, and these kind of things. So it it might take, you see like how many rows it sent overall, and it's kind of an indication of how much work it's doing. But yeah, it's a good question, right? Like how do you find whether a particular monitoring query is particularly bad? It's just about making sure that we can compare. So you can see this is the query log for the Sysmon one, where we are actually fetching Sysmon, installing it. That's just a log that's telling us what we're doing, and the data itself, these are the Sysmon events, and they are collected through the ETW here. So they're actually they're going to be collected whether the provider is turned on and off so it's more robust anyway. Cool. All right, so yeah, so we've done this, the monitor DNS queries, and yeah, we picked some kind of event, but this one's probably a little bit better, 3020. And so it's just a kind of experimental trial and error to figure out which is the which is the event that makes more sense, right? And presenting it in a way that makes sense. All right, let's go on to the next topic. So that's ETW. The next topic I have here is about volatile machine state, and this is kind of an interesting thing. For a lot of people, when I say volatile machine state, they immediately think memory analysis, capturing memory. But capturing memory is actually not the best option, because memory doesn't really cover, it's not a very good source of evidence. And we'll go into that in a minute. But when I say volatile state, it means things that change very quickly on the machine. When you take a memory image, it takes too long. And memory images are pretty slow, especially for modern servers, because the size of memory is pretty big. So, on the average, server, it might take you 5 minutes or more to take a memory image. Over that time, the system's changing, so it's actually not very good. Memory is not a very good way of getting volatile state, right? Because it's just too slow. But with Velociraptor, what we actually have is a lot of methods that are built in using APIs to get that information very quickly. And so, we have a whole bunch of plugins that are similar to the ones that Volatility has, for instance, handles, VAD, PS list, we've seen those before, and they are actually much faster and get that information quicker. So I actually think that it's getting a memory image is sort of one of the last things you should do. It's not one of the first things. So here's an example of Mutant. I mean, it's just one of the artifacts that we can collect. It's not, I don't even think it's that useful in reality, but I have a little cute little exercise to do, which probably we have time for, yeah, so it should be fine, which allows you to detect, mutants. So a mutant is basically a way of coordinating between multiple copies or multiple instances of the same binary. So you can imagine, you have a malware running on the machine, and then, it starts up. And a lot of malwares, they have multiple persistence mechanisms. So they start off from different methods. But you don't want to have, lots of copies of that process running. So you want to really make sure that only a single copy is run. And so a common way to do this is creating a named mutex. So it has a name. So that's the name, right? And that name, it makes it so that so it's unique name, right? So each instance of the program can start off and try and open this name. And when it opens this name, if it can open it exclusively, that means no other instance has it open. But if another instance has it open, then you basically can't acquire that, and then you can figure out someone else has the mutex and you can exit, right? So this is a way of kind of making sure there's only one copy. So I have a little exercise here, which is a little bit of PowerShell script to kind of demonstrate how this sort of works. So if I just run PowerShell, right, and yep, and then I just copy the program into it, then you will see that this PowerShell program starts off, and then it acquired the mutex. So this copy runs. Now, if I create another command prompt and run PowerShell in that one, and then just paste the same thing, then you see that this copy cannot acquire the mutex, right? So the mutex is running here, but this doesn't have it anymore, right? So it cannot acquire it. So then, it just kind of says, oh, someone else has the mutex, and it exits. This is kind of how it works. One copy will own the mutex and hold it for the life of the program, and the other copy will just, exit immediately. Now, the thing that makes this work is that the mutex name is kind of predictable, right? It has to be, if it was a random name, it would be difficult to figure it out, right? Different programs won't be able to identify it, right? So because it's a unique one, we can sometimes use it as an indicator. So we can use the Windows Detection Mutants artifact to try and find these mutants. So if we just search for mutants, right? So this is an artifact. And there are a couple of ways of detecting it. The first way is using handles, because mutants are just handles. They're just kind of, when you open a mutant, you kind of open a handle to it. So we have the handles plugin that just kind of enumerates all the handles. We've seen that one before, actually. And one of the ones that, one of those ones is of type mutant. One of the types of handles is called the mutant. So we can essentially enumerate all the handles in all the processes and find the one that holds that mutant that we are interested in. Or alternatively, the second way is using object tree, which is essentially a kernel level thing. So it's similar to the volatility plugin of the same name. So by default, this just lists all the mutants. And so it just kind of dumps out all the mutants from everyone. So the first way, it's going to do it two ways. The first way is using handles, and then the second way is using the WinObj. So it's going to take a couple of seconds to do that. And here it is, right? So the results came back, and we can then start to identify the mutants. But you can see that there are different processes that are holding different mutants, and they have different names. Now, if we look at the log, this is the query log, then you'll see that there's a whole bunch of these access is denied things that are happening over here, right? What's happening is that in order to dump out the handles, you have to open the process in debug mode. And a lot of processes cannot be opened in debug modes, so they can't actually, they can't really be opened. So that's a limitation of the handles plugin. Right, and then similarly, for the get object type, we can get a lot of this information from the kernel, but then a lot of it is protected, and giving us access denied and so on. So if we look at the results, this is showing us a whole bunch of mutants here, and then we can change to the other artifact. So that's the object tree. Now the object tree, it tells us all about the names that are in the global global names, but it doesn't tell us anything about the process. So we don't know which process has that mutex, but we know it exists on the system. Sometimes that's enough. The winobj method is much faster. So yeah, so normally what we would do is we would just filter it, right? Where name matches my bad mutex, right? So then we can see that we have the 2 PowerShells with holding these mutexes. Now you can also do a similar way. You can do pipes. So Cobalt Strike, for example, has pipes that it uses to communicate. And so you can do the same way, right? With pipes. Pipes are just similar to mutexes. They also have a global name, and they're used to communicate. So you can use pipes as well. But you see, this then identifies the 2 processes. There's 2 PIDs. There's the process name, and so on. So that's mutants. Okay, then we've got some process analysis. So we've seen a lot of these before, right? We've got PS lists, and we've got a whole bunch of interesting stuff to do with processes. So a PS list will give us things like the initial binary on disk. We've seen that before. It gives us the ACL token, so we know who is actually running this process. We can do the environment variables, right? So we can enumerate environment variables. Now, to get the environment variables, we actually need to parse the process memory a little bit. So there is a kind of process info is we're parsing that, and we can just dump out all the environment variables. So in this case, by default, I think it's looking for comp spec, which is the there we go, results. Let's look for anything. Just dump out all the environment variables. There we go. Lots and lots of variables, right? So for every process, and then you can see, what the so these are the environment variables in each process. So that actually affects the way the programs work. So if you're looking for proxies or whatever, then it actually can become quite interesting. And these are actually the actual environment variables that are in the binary at the moment. So if a process sets the environment variables and then launches another process, then you'll be able to see that. So it's not the same as the default variables that are in the registry. Okay, cool. So we got PS list. This is kind of information we can get from that, but we've seen these PS lists before. You can get the process call chain as well. And so currently it's not that great, but I'm just going to show you the artifact with PS3, PS3. And you can see there is a kind of a VQL here, which is recursive, and it follows, you can see that it follows the name and PID, resolving them back, to create a chain, to create a process chain. And it sort of works a little bit, but the problem is that as soon as it hits a process that exited, it can't really go past that, because it's really just looking at currently running processes. So it looks at this process, and then it looks at its parent, and then it looks at its parent, and it looks at its parent, but then its parent exited. So at some point, if a process exited, then it breaks the chain. So currently, we don't have, like there was I think quickly saw something here. That was the WMI. So for example, if you wanted to know where call chain matches WMI, for example, then it would show us anywhere in the process chain that WMI exists. Oh, this is not very suspicious. It just shows us that it starts from winning it and then is a service. That's not unexpected. But if we use the WMI trick that we did, in the previous exercise, then it will show us the full. If you recall, the first exercise was we just looked at the parents was WMI, and then the child was CMD. Now, a lot of the time, attackers will go through several steps. They'll go through a chain to try and obfuscate that parent-child relationship. So if we have detection rules that are just based on simple parent-child relationship, that won't work. So that's why the call chain is important, because then we could essentially create a detection that accounts for WMIC. Process call create. Right, so this is the thing that we did last time. Now, if we do that again through a process listing, then let's refresh that, and then filter it where call chain matches WMI, then we should be able to see this chain here, CMD with WMI. So because the full chain is shown here, right, and we have these long chain here, so we could create a better rule like cmd.exe dot plus, which is a wildcard, WMI BRBSE, for example, and that would match the entire chain, even if we had a couple of extra, things in the middle, just, because they want to make it a little bit more difficult to detect, but because we have the full chain, then we can match on that. So this is the PS3 artifact. Cool. All right. So just to sum up, we've got a couple more minutes. We can look at just the last thing I think I wanted to look at was the mapped memory. So when a process is running, it maps the DLLs into it. And the DLLs are actually mapped as copy of on write. So they don't actually load the entire DLL into memory. They're just mapped into memory. So that means that whenever a code runs on the DLL, then it will page that in. So this is just virtual memory type thing, and memory forensics is really all about this kind of analysis. So you can actually get the same kind of idea with the Vat plugin. So in Velociraptor we have a plugin called Vat, which is the same as the plugin that that is used, the same idea as the volatility plugin, except we don't really use memory analysis to get the VADs. We just use the APIs. So it means that it's much faster, and it still shows us the files that are mapped in, right? So it's basically gives us the same sort of information. So how can we use that for a detection? Well, it turns out that a lot of programs, a lot of programming environments like Python and .NET, they use libraries, shared libraries, and whenever the program wants to do certain functionality, it links in a particular shared library. And so sometimes you can get an idea as to what the program is doing by looking at what libraries it's linked, it links in. So here's an example. So this is an example of this example is showing you what the VAD looks like for different programs. And it basically shows, this is the VAD plugin. It shows you which memory region is mapped. So where it is, mapped in memory, and the protections on it, whether it's executable or read write or whatever. But probably the most interesting thing is the file name itself, right? So to see that is the file name that is mapped. So let's look at this example. And in this example, I'm just going to give you a quick idea of how you can tell what a PowerShell script is sort of doing. And one of the libraries called winHttp.dll is responsible for making HTTP calls. So what we could do, let's say that we were wondering if PowerShell programs, there is a PowerShell program, whether it made any HTTP requests. So let's create a new VQL cell and select star from PS list where name matches PowerShell. So this just looks at the PowerShell programs that are currently running. So we have a couple, right? Because I have two PowerShell examples here, right, from before. And let's just say for each of those, select star from for each of those, row equals, for each of those, query equals, select star from the VAD plugin, and it takes one parameter called PID. Okay, great. So for each of those, I'm just going to list all the VADs for that. So there's two PowerShells, and I'm just going to list the VADs. Now you can see the VADs is showing all memory regions. They don't have to necessarily be mapped, but I'm really, in this case, only really interested in ones that are mapped. So let me just add where mapping name, right? So there is a mapping, so it's not empty. And so these are the DLLs that are mapped from the disk, right? And in this case, what I actually care about are only mapping names that have the HTTP DLL in them. So if I just run this like this, there's no data because none of the PowerShell programs that I'm using are doing any HTTP things. So that they're not really linking that HTTP DLL in because they haven't done any HTTP things. But if I try and do some HTTP activity inside one of those PowerShells, so like this, PowerShell. So here I am in this PowerShell prompt here, and I'm just going to get a Google page from Google. But when I call invoke web request, it's going to go and link that HTTP plugin. right? And that means that I should be able to immediately see this PowerShell. You know, I can just add some context here, name, comma, peds, comma, staff name, ped. So I can say that's the PowerShell's program, and it's linked in the WinHTTP. So this gives me an idea of kind of what the functionality of the process is, and it's useful when you are looking for, like, let's say, an injected binary that might actually call. So the injected code itself might not come from a DLL, but whatever it's calling might actually link in things like HTTP or whatever. So it has a CNC going out. And so you might go, hey, you know, this process doesn't normally have HTTP, you know, kind of connections. Okay, can you see the URL? But that's a good question. You can't see it like this, but I think, and I'm not sure about this, but I think that there is an ETW provider, and WinHTTP.dll actually feeds in those URLs in the ETW. So there is a way of getting the URLs from the library itself through ETW. So I'll have to check on that, but I'm pretty sure there is actually a ETW provider for URLs. So all the things to do with URLs that you know will actually generate an event there. So, but that's a very good question. Can you see the URL? Okay, so anyway, that's basically, I guess the point of these last lot of slides is to try and get you guys to see that, you know, memory analysis is not usually needed or not often needed. I mean, you can do it at any time, right? Like you can get a full memory analysis, full memory image if you wanted to. So you can just go acquisition and do a memory acquisition, but it just takes so long, and it's going to generate, so it's using WinPMem. It's going to generate such a big file, you know, maybe 4, maybe 16 gigs, and then transfer it. And so that means that you can't really do it at scale, right? So, you know, it's much better to be able to do something at scale using VADs or whatever, right? Rather than, so to do the analysis again live, rather than constantly delivering that big memory image. Okay, cool. So yeah, we did that exercise. Okay, so to conclude, right, so in this module, we learned about ways that we can recover more information. We didn't really talk about the SRUM database, but we talked about Prefetch, and you know, we sort of mentioned some of the other ones. We really talked a lot about the event logs, and I think the takeaway here is, rather than collecting the raw files, it's much better to parse the event logs on the endpoint itself and then do the processing. Even if you're just forwarding all the events anyway, it's better to parse them because it's easier. We can also just enrich the event logs automatically using the messages, but you know, also just in VQL. And we can also watch the event logs, as we've seen with watch Evtx and watch ETW, the two kinds of mechanism to watch for the event logs. We didn't really cover WMI, but I think there are some skipped slides here about WMI, which you can use with VQL as well. Yeah, so I think, yeah, so is there any questions before you know, before we wrap up and on this module? The recordings of previous modules be available. Yeah, so I think all the recordings are available already. Let me just I'll just turn the recording off here.